math class already?
Calculus, early transcendentals. I can't wait to learn about calculus. You make me go mental. Logarithms aren't easy for me. When limits got you down and your mind won't work at all, don't worry about it, baby. Here comes L'Hopital. Calculus, early transcendentals, hyperbolic catenary. Calculus, learn real world models when you make it to Calculus 3.
Hello and welcome to my class. Today we are going to be talking about limits. Limits have been used since ancient times. Archimedes of Syracuse used limits in his method of exhaustion, which was a method used to calculate volumes of objects that couldn't be found using classical geometric methods. Sometime later, Newton, who might be known as the father of calculus, used limits as the foundation of methods that would be used to calculate orbits of planets, and in fact become the foundation of the subject that we now call calculus. In this lesson, we will begin thinking about this important concept.
Hello. So today we are going to talk about the idea of limits. Limits are the most fundamental thing that you study in calculus. Everything's built on limits. So later we'll talk about derivatives, and when you take calculus 2, you'll talk about integrals, and later on after that, maybe third calculus, you'll talk about series. And all of these ideas are based on limits. So it's important to get a really good, solid foundation on limits here in Calculus 1. We're not going to jump right into the technicalities of limits, but rather let's sort of introduce the idea through an example that all of us have some intuition about. That concept is velocity. The idea of average velocity is like, if something travels in a straight line, you just take how far it went and you divide by the amount of time it took. So average velocity is, we're going to call it displacement divided by elapsed time. Now displacement's kind of like how far the object traveled, but not quite. Like displacement isn't keeping track of how far something traveled like an odometer would in your car. Displacement is just keeping track of the difference between where it started and where it ended. So another way to write this formula for average velocity would be, it would be the terminal position, subtract the initial position, and then divide by the elapsed time. Now, it makes sense up here in the numerator that we can subtract because this object is moving in a straight line, and as you know, points on a straight line can be identified with real numbers. Essentially, our line gets some sort of coordinate system set up on it, and so we know where 0 is, and we know where 1 is, and that sort of thing. So anyway, so we can do that subtraction, and the terminal position minus the initial position is the displacement. Notice that if an object would go forward along this line and then maybe stop and then turn around and come back to where it started, if that happened, its terminal position minus its initial position would be 0, so it'd have 0 displacement. Even though the object moved, its average speed would be 0 because the numerator there would be 0. And that kind of makes sense because some of the times it was moving forward in the positive way, and then some of the times it was moving backwards. But in any event, let's look at, just to make sure we understand this concept with a very specific example. Let's suppose that you ride a bicycle in a straight line for 20 miles. So that's your displacement, 20 miles. And then let's say it takes you 1.5 hours. Then what was your average velocity? Well, your average velocity was 20 miles was your displacement, divided by 1.5 hours was the elapsed time. And what does that work out to be? About 13 1/3. And then the units are miles per hour. Okay, so now we want to make this a bit more mathy. You come to this class with a lot of knowledge about algebra and trigonometry, and in particular functions are going to be the basic mathematical object we work with in this class. And so let's suppose that we've got a function that's keeping track of the object that is traveling in a straight line's position on that number line. So in other words, let's suppose that we've got ourselves a position function. It's customary to denote the position function with an S. I don't know why. S is our position function, and so this function, the way it works is when you feed in a given time, it tells you what the position of the object is on that line that it's traveling along. Let me try to draw a picture of what's going on here, sort of a general picture with our position function. This line here is the line along which the object is moving, and somewhere on that line, there's position 0 and position 1, so let me mark a 0 there. And, the object is on the line, and, the object may move forward for a ways, and then it might stop and then come back a little ways here, and then it might turn around and then go back up, and then after a while it ends up here, right? Something like that. That sort of motion, we can keep track of it with the graph of a function as well. So beside this line where the object is moving, we're going to have a representation of that motion in the form of a graph. So the horizontal axis here on this graph is going to be time, t, and the vertical axis will be keeping track of the position. So, and then here's, time 0, right? So that object, if I wanted to draw a graph of it, it starts off right here, this height, because I've got it lined up with that red dot over there on the side where it starts. And it looks like, this object goes, it goes up for a ways in time. So maybe it goes up like this until it gets about here. And then it comes down for a ways, maybe to about there. Then it goes back up again. So this is our position function, s equals s of t, in graphical form. When we start thinking about calculating average velocities, we can see that both algebraically and we can see it graphically here. If you're going to have an average velocity, you got to have some elapsed time. And if there's an elapsed time, there's a beginning time and an ending time. So we call those the initial time and the terminal time. So maybe just to keep things kind of general, so we can have kind of a general formula that works, let's say our starting time here, initial time is t1. And I'm going to mark that on the horizontal axis, so the initial time, and then maybe over here somewhere else I've got a terminal time that I'm interested in. Now of course the way I've graphed this function, its true starting time was at 0, and then I didn't indicate any particular ending time for the whole graph, but maybe there's a portion of this object's journey that I want to examine, the portion of it where the time goes between t1 and t2. Of course there are some corresponding points on the position function's graph that correspond to the initial time and the terminal time. When you plug in t1, you get s of t1, and that's the initial position. And similarly, on the vertical axis there, corresponding to t2, you have s of t2, and that's your terminal time, or terminal position. We had this formula a second ago that said average velocity is terminal position minus initial position, and then you divide that by elapsed time. So in terms of this function now, we can write down that formula in a little bit more algebraic way. V average, terminal position minus initial position, so that would be s of t2 minus s of t1 in the numerator. So that's displacement. And then you divide by the elapsed time, which would be t2 minus t1. So this is the algebraic form of that equation we wrote down earlier. And there's just one more thing I want to observe about this, since we're in the neighborhood here. If we look back at the graph, those points that correspond to the initial time and the terminal time have coordinates. Corresponding to the terminal time, the points on the graph there are, well, the first coordinate is t2, and then the second component of that point is s of t2. And similarly, corresponding to the initial time, the point on the graph would be t1, s of t1. And now, if you would look at the line that goes through those 2 points on the graph, and by the way, that line is called a secant line to the graph. A secant line is a line that goes through 2 separate points on the graph of a function. So we could look at what the slope of that line is. Remember from algebra class, the way that you calculate the slope of a line, if you know 2 points on that line, you just have to take the difference in the y coordinates and then divide by the difference in the x coordinates. But when you look at our formula for average velocity, you see it's doing exactly that. The numerator, s of t2 minus s of t1 there, is the difference of the y-coordinates of those points on the secant line, and the denominator is the difference in the x-coordinates. So really, little observation, v average is equal to the slope of the secant line from t1 comma s of t1 to t2 s of t2. And usually when we talk about the slope of a line, we use the letter m to denote that. So here m sec will be the slope of the secant. So this is kind of cool because now this velocity concept, this average velocity concept, we have a geometric way to think about it. And having multiple ways to think about things is helpful sometimes. It gives you a good idea how to, sometimes gives you different points of view, different lines of attack when you're trying to think about it. So let's keep that in the back of our mind. If you see an average velocity, it's really, when you look at the graph of the position function, has to do with the slope of a line. We're wanting to talk about limits. We're trying to introduce the idea of limits. Average velocity is, this thing that happens over a long interval of time. But when an object is traveling, like if on this bicycle ride in this example, the bicycle rider average speed was 13.3 miles per hour, but that doesn't mean the bicycle rider was always moving 13.3 miles per hour. It just means that on the average, that was his speed. Perhaps sometimes, the bicycle was going down a hill and it started going fast, maybe 25 miles per hour. And there were other times when the bicycle rider was going up a big hill and it was only going 5 miles per hour. And so it kind of got 13.3 in the average. We want to start thinking about instantaneous velocity. That's the speed that you have just at a moment in time. It's not over an interval of time, but rather at a precise moment in time. So if you think about this, driving a car, it's the speed that you see on the speedometer. That's telling you how fast you're going at each moment. So we want to somehow go from, how can we use the concept of average velocity to get to instantaneous velocity? I want to think about that as we're doing this next example. So in this next example, let's suppose we got a ball that gets launched straight upward with a certain speed. In this case, it's 96 feet per second. If you neglect wind resistance, physics tells us that the ball, we can actually predict what its height would be at any particular time. And it turns out, through magic of, turns out to be calculus, that we don't know yet, but you can deduce that the position function has to have this formula, negative 16t squared plus 96t feet after t seconds. And so I took the liberty of going ahead and graphing that function here. And it's a parabola. And that object, so this graph is telling you the object starts at height 0, and then as time increases up to 3, it's going upward, and then at about 3 seconds, it starts coming back down again. This is our position function. And I just want to play with our formula that we came up with a little bit ago and think about some different average velocities. But I also want to tell you that I'm interested in this instantaneous velocity thing, and I'm going to pick a particular point here. Let's say when t is equal to 1. Which corresponds to this point on the graph right here at about height 80. I'm going to be interested in what is the instantaneous velocity whenever time is equal to 1 second here. I haven't told you how to do that yet, so the point of this example is going to be to build up to how do we answer that sort of question. To get us thinking in that way, I want to make a little table of average velocities over intervals of time that start at 1 and go up to some other time t. So the initial time is always going to be 1, and then the terminal time will be sometime later than 1. And then I want to look at the corresponding average velocities. And remember, our formula for that would be, well, here we have our initial time and terminal time. The initial time is 1 and the terminal time is t. So remember, our formula was terminal position minus initial position. So that'd be s of t minus s of 1, all divided by the elapsed time, which would be t minus 1. In this table, let me put in a few values here. Let's see. Let's go maybe 1 to 3, 1 to 2, 1 to 1.5, 1 to 1.1, 1 to 1.01, and maybe I'll do one last one here, 1 to 1.0001. Now, when you think about these intervals, as you go down this table, you can see that they're getting shorter and shorter. The idea being is that by the time you get to the last interval, Like that last interval is practically a moment, just a single moment in time, right? Now it's not really just a moment in time. It's an interval. It's just a very short one. I mean, it's 1/10,000th of a second long, that interval. So for us humans, we won't even perceive that amount of time passing. I want to see what happens to these average velocities as we start closing in on a moment in time. And it turns out that this sort of process of refining and making smaller and shortening our interval of time, so this is the actual idea of a limit that we're trying to get to in this whole chapter here. Let's calculate those average velocities. In the interest of time, I think what I'm going to do is just compute all these, and then I'll edit out the, doing all this computation. But, if I want to do that first interval, just to make sure that you're following along what I'm getting ready to do, for the interval 1, 3, I'm just going to plug in, I got to do s of 3 minus s of 1 over 3 minus 1. And so then, I got to do what? Negative 16 times 3 squared plus 96 times 3 minus, then I plug in 1, and I'd get negative 16 times 1 squared minus 96 times 1, and then divide all that by 3 minus 1, which is 2. And then, keep on going and simplify that down to a single number. So I'm going to take a second and probably just go to my handy-dandy calculator and plug all these in, and I'll be right back. So I'm back, and I have filled in the table on the right. And now what is this telling us? Well, we've got a bunch of average velocities there. The average velocity over the interval from 1 to 3 came out to 32. Of course, the units here, the position function was measured in feet, so that's the numerator, and the time was measured in seconds. So our units on each of these would be feet per second. The second interval, 1 to 2, was 48 feet per second, and so on. You see, as those intervals getting smaller and smaller close to 1, so that we're practically looking at the moment of time at time t equals 1, looks like it's getting close to 64. So that's the answer that I was looking for. Now, at this point, it's just an educated guess as to what the answer is, but for now, that's enough to convey the idea. So the answer to the question it'll be 64. Anyway, that's our conjecture. But it turns out, that's the right answer. A little notation that we're going to do here to indicate that this answer of 64 was the instantaneous velocity. I'm going to use this notation, VINST equals 64. To indicate how I got that answer, I'm going to say V instantaneous velocity. The way we obtained it was as a limit, LIM, as the values of t were approaching 1. We'll indicate that underneath the lim symbol. And then what were we taking the limit of? We were taking the limit of these average velocities on the interval 1 to t, which algebraically looked like this: s of t minus s of 1 over t minus 1. The real notation that I wanted to introduce here is this idea of the limit. By looking at that table, notice that those values of t in this table were getting ever closer and closer to 1. So that's why you see under that, in that notation for the limit, t with an arrow pointing to 1, we're indicating that the variable that we were playing around with in this problem was getting close to 1. So that's the idea of limit. It's when you take a variable and you make it get really close to some fixed value without ever letting it get all the way there. Now you might think about why we don't let t be just exactly equal to 1. Well, what would happen in that formula on the bottom right if you would try to plug in t equals 1? Well, when you look at this spot right here, the denominator, if you tried to put t equal to 1, you'd be dividing by 0. So it's not a matter where we can just simply plug in t equals 1 and get the answer. We have to put in values of t that are very close to 1 and see what it's getting close to. And if it does get close to something, we say that the limit exists. And sometimes when you start plugging in these values that are close to 1 or whatever, it just goes like you just get a bunch of craziness. So that's the idea of a limit in sort of by examining a table. Now when we're really doing these things later, we're going to come up with algebraic ways of calculating these limits where we don't have to look at tables and plug a lot of things into calculators, because that's very cumbersome and takes a lot of work. Let's do another example. But first, let's have a little summary of what we've talked about. If we have a position function and then we have an initial time at t0, so initial time is t0 and a terminal time t1, and I can look at the corresponding points on the graph and draw a line through them. I can write down the coordinates of those points. And that green line, when you look at the slope of that line, you get the average velocity. So V average is S of t1, the terminal position, minus S of t0, the initial position, over t1 minus t0, that's the elapsed time in the denominator. And then if I want to do the instantaneous velocity at the point t equals 0, let's say, then the V instantaneous would be our limit. As we put in values of t that are getting closer and closer to the t0, the expression that we plug the values of t into are the average velocity formula. So it'd be S of t minus S of t0 over t minus t0. And you can plug just about any values of t that you want to into that formula, except for you can't set t equal to t0, because then that would make it 0 in the denominator. As we already saw, the average velocity is really just the same thing as the slope of the secant. And remember, we had this notation m secant. So that line that goes from t0, S of t0 to t1, S of t1 has that same formula, S of t1 minus S of t0 over t1 minus t0, that you have for the average velocity. Now there's one thing here that we didn't talk about yet, and we're going to go back to the previous example and talk about it. The idea of a tangent line is something I want to talk about. So let me go back for a second to this previous example. We had all these intervals of time in this table that we know correspond to secant lines. So the first interval that we did there was interval from 1 to 3, and we could look at that secant line there. And for that one, the secant slope in our table we could see was 32, because that's the same as the average velocity. And then we did another one when t was equal to 2, and then we had another secant line here, and its slope was 48. And that makes sense on that picture, right? Because the second line that I drew has a steeper slope. You know, by the time that you do that last interval, you know, you've got a right-hand endpoint that's very close to 1. So when you try to graph that second point, it's practically setting right on top of the first point that you graphed at t equals 1. And so when you graph that line, it gets ever closer and closer to what we call the tangent line. So the red one here is the tangent line. The thing about the tangent line is that it just touches the curve at that one point when t is equal to 1. So this point right here, 1 comma s of 1. The tangent line just touches the curve at that point and not the other ones nearby. If the tangent line just touches the curve at that one point, you can see why it's difficult to find the slope of that line, because if you're going to find the slope of a line, you need 2 points on a line. But with a tangent line, you're only given 1 point on the line. So how are you going to find a slope? Well, I think from this picture, it's kind of geometrically evident how you might want to get the slope of that tangent line. The tangent line is very closely approximated by a secant line over a very short interval, right? So the secant line for that very last interval that goes, that corresponds to 1 comma 1.0001 interval, that line would be, to the naked eye, indistinguishable from the tangent line. And so again, the idea here is that the secant lines seem to be kind of closing in on the tangent line, right? The slope of the tangent line is exactly the same thing as the instantaneous velocity. So m tangent, let's call it, for the slope of the tangent, is also going to be the limit as t approaches t0 of s of t minus s of t0 over t minus t0. So even though we're thinking about the slope of the tangent as a geometric concept, it's the same as this dynamical concept of instantaneous velocity. So we're making a connection between the geometry of the curve and like some interesting property of the function that we're interested in this case, velocity. A little later in the class, this thing is going to be called the derivative. And the derivative turns out to be the subject of the rest of the class after we talk about limits. So another quick refresher example, just to make sure we're understanding things. So here we have another function that tells us the position of an object moving in a straight line. This time our position function is negative 4.9t squared plus 30t plus 20. And I have two questions set up here that I want to answer. One is to find the object's average velocity on the interval 0 to 3. And then I want to find the object's instantaneous velocity at time t equals 1. Let's go ahead and do the average velocity. I think that's the easier question. So v average on 0 to 3 would just be the displacement, s of 3 minus s of 0, over the elapsed time, which is 3 minus 0. And now I can take those numbers and put them into that function and get an answer. That comes out to 15.3. And notice in this example that I didn't give any units for the position function, like whether it's feet or meters or whatever, and I also didn't give any units for time. Now let's think about this instantaneous velocity business. For that, I think I'm going to, just like I did before, do a little table. I would highly recommend that you push pause on your video and see if you can come up with a little table that gets you the instantaneous velocity and see if your answer matches what I come up with. So the way I'm going to do it is to do, let's see, intervals from 1 to t, because I want to do the instantaneous velocity at 1. By the way, it would be okay to do intervals from t to 1, where 1 is the terminal time too. Doesn't really matter. Should get the same answer. And then I'm going to do my v average in this table, which is s of t minus s of 1, t minus 1. And I think I'll do like 1 to 2, 1 to 1.1, 1 to 1.01, 1 to 1.001. So I'm going to run to my calculator and calculate these things and come right back with the table filled in. From examining that table, that my v instantaneous velocity. So my guess, this is really just more of an educated guess than anything. Now it turns out to be exactly the right answer, but from just looking at a table, you only really have kind of a guess at the right answer. But it's going to turn out to be about 20.2. And the good news is, though, we won't have to guess for very long. We'll have some techniques that give us exactly the answer on the money. All right. So one last little example, maybe to tie in this idea of tangent lines. Instead of thinking about velocities and time, here I just have some function, y equals x squared, and I have a particular point, and I want to know what is the slope of that line that's tangent to the graph of y equals x squared at that point, x equals 1. The thing that I'm trying to find is the slope of this line that's tangent to the graph at 1. So that means it just touches the graph at that point, 1 comma 1 squared, which is just 1 comma 1. And it doesn't touch the other nearby points on the graph. What is the slope of that? And you see the problem again. If I want to find the slope of a line, I really need 2 points on that line, but I don't know any other points on that line. I just know 1 comma 1. So this trick of using a limiting process is pretty cool. So what we're going to do is think about picking an arbitrary x value here somewhere to the right of 1. And you could have picked it to the left of 1 too. It would work if you did it on either side. And instead of looking at the tangent line, I'm going to look at the secant line that goes from here to here, like so. Now, what would be the coordinates at that second green point on the right, corresponding to x? Well, the x coordinate would be just x, and the y coordinate would be what you get when you plug it into the function, which is x squared. So the slope of that secant line is the same as the average velocity, so I'm going to be looking at intervals of the form 1 to x, and then I'm going to look at the slope of the secant corresponding to the points on that interval, which would be x squared minus 1, the difference in the y coordinates, and then over x minus 1, the difference in the x coordinates. And then I'll look at, say maybe from 1 to 2, 1 to 1.1, 1 to 1.01, 1 to 1.001. I'll stop there. I mean, I could keep going forever, I suppose, but you have to stop somewhere. So if you do this for 1 to 2, it comes out to 4 minus 1 over 1, so that just comes out to be 3, right? And having done this before, I know ahead of time that this is going to come out to 2.1 here, and this will come out to 2.01, and this one will come out to 2.001. And so, what is happening here? As the x here gets closer and closer to 1, what's happening to values in the right side of the table? Looks like to me they're getting close to 2. And it turns out that's exactly what the slope of the tangent line is. So the m tan is going to be 2 based on the work that we did in the table over there. Well, hopefully this idea of limit, where we have a variable and we let it get closer and closer and closer to some fixed value. In this last example, our variable was x, and the values of x were getting closer and closer to 1, and we were seeing what that caused to happen in this algebraic expression here. And it turns out that that algebraic expression started getting closer and closer to 2 as the value of x got close to 1. And so what we did was we did the idea of the limit, right? This 2 that we came up with here was the limit as x got closer and closer to 1 of x squared minus 1 over x minus 1. So hopefully this idea of limit just has a little bit of intuition for you right now. You understand, okay, all I'm doing is letting one variable get close to some specific value without ever letting it get equal to that value. And again, in this particular example, we couldn't let x be equal to 1 because we'd divide by 0 if we did that. But we could let x get really close to 1, and that's the idea of limit. Okay. Well, that's all I have for you today. And I'll look forward to talking to you again soon in another video. Bye now.